concentrate on, how would such an environment or a bath look like? And what do we know about the bath? And how can we play around with the bath? And what does it mean coupling to and decoupling from a bath? And especially I want to show you that we can build baths that basically remember completely what you put in after a specific time. And in between, they look completely classical. So there's some time where they're completely like a classical bath that you ever wanted to know, that everybody uses. But at specific times, they know exactly what you put in. They completely recur, if you design them correctly. And we'll show you. So the motivation to talk about that part here in that conference is that, an example of things that we've seen many times here is that, I have a cold bath and working fluid and a hot bath. And I want to look at that in an aspect where these things are not simple harmonic oscillators, but it's a quantum many-body system, a small system of a few thousand particles, and see if there is, what are the different types of things we can build with that. And as you will see that would be one-dimensional systems, and you can couple them, decouple them. There will be, parts. And I will basically look at the role of one of those things, of a simple, what's the role of the bath? Let's first go back historically. Poincaré in 1890 basically said that any finite system, physical system, will return arbitrarily close to its initial state in the course of its dynamics. Now, if I build a machine with a bath, this bath is always finite. So it's a valid question to ask yourself if you want to build a machine like that, what is the time that the thing will come back? Because that would mean it remembers exactly how you couple it. So it's the maximum violation of being, Markovian that you can imagine. Now, this thing was then, picked up by guys in the end of the 50s, the 60s. They basically formulated, Poincaré and Percival formulated that these occurrences, something similar than Poincaré's conjecture, and how they can happen in the quantum domain. And of course, in the very simplest form, I think these occurrences showed up in the James Cummings model, and there were beautiful experiments. And there was predicted already early in the 60s by Cummings itself, and there was a whole set of experiments by Harosh, Rempe, and others that showed that in a very simple system of very few modes, you can see these recurrences. Now, with the advent of Bose-Einstein condensate and a much more elaborate ways of doing experiments, I think we can think of what is happening now in a real interacting many-body system, because in this James Cummings model, the photons are non-interacting really. Yeah, it's just occupation numbers of bosons. So in principle, if an interacting system, you can write down your wave function in the form of a sum over of many-body eigenfunctions that each have its energy ak, and you would mean in a Poincaré sense, you would have that the recurrence occur when the wave function at time t and a wave function at time t plus tau, this product is in the order of 1. Now that requires that I can measure these wave functions, that I can have a resolution in my experiment that can do that, and we'll come back to that. Now, if all dynamical phases have to be close to multiples of 2 pi for that to happen. For a few-body system with very few populated states, this can be achieved, and there are beautiful experiments that were done in the Bloch group by Greiner and by Sebastian Will, who showed that for 3 atoms in an optical lattice site. Yeah, and then basically they had these atoms be populated in a coherent state there, and if alpha squared was 3, they could show that you can see them recur. Now, if my system is much larger, I can ask yourself, of course, in a very large system, this recurrence time becomes exponentially large, but also it's exponentially difficult to observe these states. Yeah, and I will give you all the way in the end and hint how exponentially difficult that is. Yeah, and also if you think about, it's very difficult to Rainer blood, which basically hits a really hard wall if he wants to make tomography with more than 10 qubits. Yeah? So that tells you how complex it is to measure it. So as an experimentalist or as a physicist, you basically don't have a chance of measuring a many-body eigenstate, except if it's a ground state and there's a huge gap. But in the usual system, you don't have the chance to do that. What we do is we make much simpler experiments. We make much simpler experiments, and these are few-body observables. They might be local, they might be non-local, whatever, but they make few-body observables. Therefore, I think one has to, if you talk about recurrences, you have to think about the question is that, can I observe an occurrence? If I want to observe an occurrence, I have to ask the question not, does the wave function come back exactly to what it is, but does the wave function come back under the assumption of my experimental measurement that I can do? Yeah? So I have some operator O, which is usually related to some kind of an collective mode or some modes in a low-energy effective quantum field theory describes my many-body system. And so I basically have to think about, does this, do these things come back under these observables? Yeah? So the system does not have to come back close to its initial configuration completely of many-body states, but only needs to satisfy the condition that gives similar results on some observation O. Because this is, I can do nothing else. Yeah? So the other question is an empty question. Yeah? So now, in quantum many-body systems, such as I said, such observables O can be chosen to reflect the collective degrees of freedom of my system. And these are the collective degrees of freedom of my system that basically described the underlying, low-energy effective quantum field theory describes my system, some kind of a way that I extract out of my microscopic Hamiltonian all the relevant quantities in an RG sense and describe it by an effective theory. Now, and these operators, can you relate to these, to the real quantity? These are the good measurements you can do are the ones that are related to these collective degrees of freedom. And this way, how to do that, dramatically reduces the complexity of my problem. Yeah? And now, it reduces this to the number of populated modes in the same way as you would, and it's not the number of complete degrees of freedom of the microscopic degrees of freedom, which I can't see. And then, of course, I can design my system in such a way that these modes, if these modes become commensurate, then I can observe recurrences. And that's exactly what I will show you how to do that in an experiment for a system, many-body system that's interaction dominated, but has 5,000 particles. So the largest quantity is the interaction energy in the system. Yeah, and we show you how this can observe recurrences in a system like that. Good. First of all, the outline of my talk. First, I'll talk a little bit about, what's the system that I study. It's a one-dimensional quantum fluid. And then we do that on an atom chip. And we observe these recurrences. And how do we observe the recurrences in coherence? I will talk a little bit about the quantum non-equilibrium evolution, just to give a very quick overview to show you what is the basic thing. And then I will show you how you can basically observe recurrences in an inverse light cone and where the long-range order comes back. And in the end, in the outlook, I will maybe say something about what this might mean. So the system we look at is a one-dimensional quantum gas. It has, bosons sitting in a trap. It has a longitudinal trapping and a transverse trapping. And if the interaction energy and the temperature is much smaller than this transverse trapping frequency, you basically, the only accessible degrees of freedom of the system are in 1D and are these along this direction. For that, you basically can describe it in most of the cases as some kind of an fluid, which has where the wave function, the minimal wave function, can be described in the form of a fluctuating phase and a fluctuating density. And this fluctuating phase is very easily accessible in the experiment by interference. These one-dimensional systems are interesting also from a theoretical point of view, because in principle, if you take in hardcore bosons in an exactly one-dimensional system, this is the Lieb-Lininger model, and it's exactly solvable. And the Lieb-Lininger model has very complicated constants of motion and things like this, but you can make a low-energy effective theory, which is a Luttinger liquid, whose excitations are phonons, or sound waves. There's a linear dispersion relation, and this model is a model basically for relativistic quantum field theories. And then if you take two of those systems together, you could couple, you could create the Sine-Gordon model as you know, Eugene Demler and Vladi Gritsev and companies have showed you. And this model adds to the lattice liquid model a non-trivial term here for the quantum fields. And that's a strongly interacting quantum field theory with topological excitations and many other things, and you can play around with that. But for the moment, in the beginning, I will basically stuck into the lattice liquid, and we'll talk about that. We build our 1D systems on this chip, where we can create extremely elongated traps, where the transverse size is about 100 nanometer, the length is about 200 microns. We can have experiment with a few hundred to a few thousand atoms in there. The temperatures that are 10 to 100 nanokelvin. The temperature is something like 0.1 times h bar omega transverse trapping frequency, and the temperature is about 0.2 times interaction energy. So the systems are the largest part, by a factor of 5, is interaction between the atoms. It's a complete interaction dominated system. Then this system is, in that sense, is nice. We can split it from 1 into 2, and we can observe the fluctuations of the phase between the two systems by interference. In that sense, it's a beautiful way that we can basically measure this fluctuating part of the order parameter of the wave function of the phase. And over the years, we have developed many different methods together with Eugene to develop, and his students, to really how to analyze these type of things. Now, if we do an experiment in this very simple and fast way, you take one single system, you make a quench, bring it out of equilibrium and split it into two. And what does a quench do? A quench is a beam splitter, and as a beam splitter as such, if the quench is much faster than the interaction energies in the system, then I can completely ignore for the quench the interaction energy, and this is like a beam splitter that I apply. So the phase is an exact copy of each other, but there are local fluctuations in the density. And I can then I either look at the system left or the system right, or I can look at the symmetric or the antisymmetric mode. And if you look at the symmetric mode, that's given by the thermal population of the original system, and the antisymmetric mode is only populated by the quantum fluctuations created by the splitting process. And it's interesting to know they have a method here that in principle the antisymmetric mode is in